Hello, my name is Yves Como, and I am a professor at Polytechnique Montreal, Quebec, in Canada. It is my pleasure to present this open access video course on microbiology and metabolism, which is part of the Biological Wastewater Treatment online course series organized by the Global Sanitation Graduate School, which is under the Institution of Higher Education of UNESCO, based in Delft in the Netherlands. The title of my presentation is Microbes in Process Optimization, from Physical to Chemical to Biological Insights. In this video, I will present the order in which biological unit processes should be optimized, which is to first look at physical, secondly at chemical, and thirdly at biological factor. 3 short case studies will be presented to illustrate this concept before presenting a mind mapping of factors affecting bioprocesses. 3 more specific examples will then be presented before concluding this presentation. Anyone who is trying to understand, optimize, or design a biological unit process should follow the order of bioprocess optimization, which should be to first look at physical processes, then at chemical processes, and finally at biological processes, in that sequential order of physical, chemical, and biological processes. This is what I will illustrate in the rest of my presentation. Here is a first example of an operational problem to which potential causes and solutions are presented. This photograph shows the effects of grit accumulation on an aeration tank floor, which is obstructing and damaging diffusers. This picture, like others in this presentation, was taken from a chapter of the book of Chen et al. 2020, which is available as an open access document and which can be reached by clicking on the hypertext link. The potential cause of this problem is grit accumulation that affects aeration efficiency in the bioreactor and reduces the liquid volume. This problem can be fixed by a physical approach of improving degritting, a physical unit process, in the pretreatment step. A second example of an operational problem with its potential causes and solution is illustrated in this picture, which shows rising sludge in the secondary settling tank of an activated sludge plant in Brazil, affecting effluent total suspended solids and sludge inventory in the process. 3 potential causes can be proposed with the respective categories of solutions. First cause would be that denitrification is taking place in the sludge layer of the secondary settling tank, which was the case in this particular cause, in this particular case. A physical solution would be to add a recirculation loop into an upstream anoxic zone to remove oxidized nitrogen, nitrate and nitrite, and this would achieve 2 biological functions of reducing the presence of both biodegradable COD and oxidized nitrogen in the secondary settling tank. A second potential cause would be that methanogenesis is taking place due to anaerobic conditions in the secondary settling tank sludge blanket, producing biogas bubbles. A physical solution would then be to increase mixing and aeration in the upstream bioreactors, which would achieve the biological function of reducing the presence of biodegradable COD in the secondary settling tank sludge blanket. A third potential cause would be that filamentous bulking is taking place. A short-term solution for this problem would be to use a chemical approach to oxidize filamentous organisms by adding oxidizing agents such as chlorine, ozone, or hydrogen peroxide. A longer-term solution would be to increase the substrate over biomass ratio by installing a short hydraulic retention time upstream selector, which could be aerated or not, to preferentially feed non-filamentous microorganisms. A third example is related to fouling control of membrane bioreactors, for which a designer needs to provide flexibility for physical, chemical, and biological factors. This figure illustrates how the components of a membrane bioreactor interact from the wastewater, which allows the growth of sludge flux in the activated sludge, which are largely retained at the surface of the membrane, allowing the filtrate to pass through along with some colloids and solutes, but leading to its gradual fouling. Let's look at physical, chemical, and biological factors in sequence. Physical factors that should be considered for this process, for this fouling control, include pre-treating the wastewater by using ultrafine screens, sludge modification by optimizing the hydraulic retention time, optimizing hydrodynamic conditions such as intermittent aeration, scouring, automatic aeration, mechanically assisted aeration, and granular activated carbon addition. Physical cleaning by backwashing, relaxation, vibration, and ultrasonic cleaning, and subcritical flux operation. Chemical factors to be considered include sludge modification by using coagulants or adsorbents, and chemical-intensive cleaning by chemically enhanced cleaning, cleaning in place, and intensive cleaning. These approaches can be used for both maintenance or recovery cleaning. A biological factor to be considered is sludge modification by optimization of the sludge retention time. Mind mapping allows to organize concepts of processes for biological wastewater treatment. This overview illustrates how suspended growth or biofilm unit processes can be studied by looking at influent characteristics, both concentration and loading, and at processes that are physical, chemical, and biological, and at factors affecting bioprocesses. Let's have a more detailed look at each one of these groups of factors. Influent characteristics can essentially be split into the various components of trash, which is coarse matter, grit, such as sand, and other dense material, influent COD, which can be divided into biodegradable and unbiodegradable fractions, inorganics, notably for drinking water sludge, which could contain chemical components with some coagulation potential, and coagulants that can be added for phosphorus removal, notably. Mind mapping of physical processes for biological wastewater treatment allows to divide them into the following categories, among others that you could add to this list, such as screening to remove coarse material, hydraulic retention time to provide the required reaction time in the various reactors with a number of factors to consider, such as flow rate, liquid volume, dead volume, notably due to grit and sludge accumulation, and ice cover if applicable. Settling to ensure proper physical separation in primary or secondary settling tanks or in sludge thickeners, with factors such as hydraulics, sludge concentration and characteristics, and coagulant and polymer addition. Aeration to provide oxygen to the biomass, with factors such as liquid depth, aeration intensity, bubble size, and various oxygen transfer factors. Mixing to ensure efficient mass transfer between reagents with factors such as aeration, mixing under unaerated conditions, basin hydraulics, density currents caused by temperature or salinity gradient, and biogas production. Filtration that can be granular or membrane-based, and adsorption to remove organic or inorganic compounds. Mind mapping chemical processes for biological wastewater treatment allows to divide them into the following categories, among others. Coagulation, which will be affected by the coagulant type and dose, and is often used for phosphorus precipitation with cations such as iron, aluminum, magnesium, or calcium. Flocculation will depend on the polymer type and dose. Disinfection, which is achieved by chlorination, UV photolysis, ozonation, which also brings the benefit of degrading some components of chemicals of emerging concern. Inorganic oxidation of reduced iron and sulfur, which could increase oxygen requirement. And base or acid addition, which can be used for pH control. Mind mapping biological processes for biological wastewater treatment allows to divide them into the following categories that illustrate the metabolic diversity of the trophic groups of microorganisms, which is illustrated on the figure on the left. A first broad division between groups of organisms is related to carbon anabolism, illustrated by the bottom left arrow. This carbon comes either from organic matter for heterotrophic organisms, such as humans, or from inorganic carbon, such as carbon dioxide, for autotrophic organisms, such as plants. A second broad division between groups of organisms is related to energy metabolism, the second red arrow on the left, that either comes from chemicals for chemotrophs or from photons from light for phototrophs. Electron donors can be organic for organotrophs or inorganic for lithotrophs. Electron acceptors can be oxygen for aerobic organisms, including BIOP organisms, also called phosphorus-accumulating organisms, nitrate for denitrifiers, which includes some PAOs, phosphorus-accumulating organisms, nitrite for anammox organisms, sulfate for sulfate-reducing organisms, organic compound for hydrolysis, such as protein for ammonification, fermenting organisms, or acetoclastic methanogens, while it is CO2, carbon dioxide, for hydrogenotrophic methanogens. Photosynthesis uses various types of electron donors and produces or not oxygen. Understanding these biological processes allows to identify which compounds affect different processes and conversely, which processes affect different compounds. A number of factors affect physical, chemical, and biological processes. The concentration of biomass, electron donors, electron acceptors, various nutrients, protons, for pH, which affects many reactions such as fermentation, nitrification, and denitrification, and inhibitors all play important roles. Temperature and mass transfer from mixing, aeration, or biofilm thickness also affect processes. For example, the photograph of a biofilm plastic carrier is shown, which need to be suspended in a liquid media with some turbulence to ensure, first, that organic matter, nutrients, and electron acceptors are fed to the biomass, and second, that the biofilm remains thin enough to prevent clogging and to ensure efficient mass transfer. An example of understanding how processes affect a state variable can be done by using a stoichiometric matrix, which is commonly used for modeling biological wastewater treatment processes. In this example, the oxygen concentration can be seen to be affected by the activity of 3 groups of organisms for a total of 7 aerobic processes, which are the growth of ordinary heterotrophic organisms on fermentable substrate or volatile fatty acids, the activities of phosphorus-accumulating organisms for the consumption of PHA, the storage of polyphosphate, the formation of glycogen, and maintenance, and for the growth of nitrifiers. For example, a probe showing a sudden increase in oxygen concentration could indicate an inhibition of a biological activity due to substrate limitation or the addition of a toxicant. The same stoichiometric matrix can be used to examine the effect of various state variables affecting a process. The result is the stoichiometric equation of a reaction. For example, the aerobic growth of ordinary heterotrophic organisms on fermentable COD, reaction number 4, uses the reagents oxygen, fermentable COD, ammonia, and orthophosphate to produce carbon dioxide, heterotrophic biomass, and total suspended solids. Any reagent limitation would reduce the rate of the reaction. A final example is given to illustrate the proper order of bioprocess optimization. If nitrification were to be observed to be lower than expected in a biofilm process, modeling solutions could be first, to decrease the maximum nitrification rate, which is a biological factor, or to consider that mass transfer effects should be dealt with by dividing the biofilm into multiple layers to better account for mass transfer limitation, which is a physical factor. It would be erroneous to consider biological factors prior to physical factors. It would be advisable, however, to first consider the physical factor before the biological ones, following of the order of physical, then chemical, then biological processes for bioprocess optimization. In conclusion, it is recommended to use the sequential physical, chemical, biological approach for improved understanding, operating, modeling, and design of bioprocesses. I thank you for your attention.